Welcome again. We will commence now our CPD Talk number 12 today. And this will be focused on building isolation using elastomeric bearings to mitigate the impact of vibration and noise from railway, essentially, and enhancing comfort levels in the building design. Getzner is a leading global specialist in vibration isolation in the railway, construction, and industry sectors. They differentiate themselves by using material that they have developed in-house to effectively reduce vibration and noise and maximize the longevity of those materials in line with sustainability goals. And from Getzner, I have three colleagues joining us today. Omar Malaz, who is with us here in the room in Harriet Watt. Omar is an area manager in Getzner. He is a mechanical engineer with long experience delivering vibration mitigation solutions in the industry, in the energy, water, and building sectors in our region. So Omar will be supported by two colleagues who are joining us online. Ulrich Gerhaher, who is a product developer in Getzner. Ulrich is a civil engineer with a PhD in elastomeric bearings. For 9 years, he has been the leading expert on bearing for vibration isolation of buildings. Thank you for joining us, Ulrich. And another colleague will be also supporting today's presentation, Andreas Wenz. Andreas, he's the lead project engineer, particularly for the Optineo project, which will be presented today. And Andreas has also got a long 10 years experience in building isolation in Getzner. So before I move to the team, I wish to thank our sponsor this year, Hampel, who is a supplier of intermittent fire-proof and durability paint. And that's it. So I will now hand over to Omar, please. We will go with the presentation for around about 45 minutes and take the questions at the end.
Yes, good. Thank you, everyone. Thank you, Iman. Thank you, the team. Thank you, Hemant. Also, thank you, Institute of Structural Engineering in UAE for this opportunity. Thanks for everyone for taking the time to share with us today and share with us a platform to introduce this topic, building isolation. Today, we would like to address this topic. The main target is to introduce the problem, introduce the solution, and a very interesting case study we have from Germany. We are increasing the value of buildings and their comfort levels by offering protection against ground-borne railway vibrations. Thank you, Iman, for introducing the team and I. If my colleagues would like to say a few words about themselves or just to say hello, please feel free.
Hello, Ulrich Gerhaher, my name. Yeah, I guess I was introduced good enough. I'm working for Getzner 10 years now.
I don't think we can hear you, Ulrich.
Oh, microphone is switched in.
Online, but not okay.
Sorry, you can't hear me?
All right.
Hello?
Oh, okay.
Okay.
I can hear him.
We can hear you online, but we can't hear you here in the room, so it's fine. But okay. Anyway, thank you, gentlemen. Thank you, Ulrich. I will proceed with the agenda. So I will be introducing first the topic of vibration isolation. How are the roles and responsibilities distributed in a project between the different stakeholders and also Getzner? Then we can talk about a case study, the Optineo, share an overview about it, including the legal situation, the project limits, so how were the measurements taken, or some brief information about the measurements and the prognosis modeling. How does the solution actually look like on site? and what were the results of the measurements at the end. So by starting just to introduce the topic, this is what you see on the screen is a project in Berlin, which provides a perfect example for the need of elastomeric or elastic building isolation. Here you can see a railway line directly adjacent to a construction site. Of course, there are vibrations occurring every time the train passes by the building, and the vibrations are transmitted as structure-borne noise through the ground and then into the construction site. This project actually shows an example of a full-surface elastic decoupling with our products, which is in this project we use the Silodyne product, which is a polyurethane bearing. Like Iman said previously, Getzner has developed in-house. These products are shown in green, yellow, and red, and are designed and installed to provide an enhanced comfort to the building occupants by absorbing the vibrations and disturbance caused by the source. So in a nutshell, this is what Getzner does. We manufacture these highly advanced polyurethane products that are highly advanced elastomeric products for the purpose of vibration isolation in buildings and also other sectors. It is important to distinguish between primary airborne noise and secondary airborne noise. The primary airborne noise is that which is transferred directly from the source, which is in this case the railway, to the recipient, which is the building, through the air. While the secondary airborne noise is the result of the vibrations that are transferred from the source through the structure and the ground into the building, and then causing vibrations within the building that in turn transfer to what we call secondary airborne noise or structure-borne noise. So our company and our expertise, and in this presentation, we are addressing the topic of building isolation against vibrations and secondary airborne noise from railway lines that are coming from railway lines into buildings that are still in the planning and the design stage. So there are several solutions from Getzner available. The bearings can be applied as full surface mats or as strip or point bearings, depending on the various site and design conditions. Just to briefly describe each solution, the full surface bearing is basically a full surface mat that's very easy to shape and install. It should achieve lower natural frequencies, i.e. lower performances compared to the point and the discrete bearings. At the same time, little soil preparation or subsoil preparation is required when installing such type of material in such geometries, and no changes to the structural design is required when installing a full surface mats. On the other hand, strip bearings are usually installed on strip foundations. It provides the ability to achieve vibration decoupling between individual floors of a building. It is cheaper than it's more affordable than a full surface mat material-wise, and it achieves lower natural frequencies, i.e. higher performances. At the same time, it requires special structural designs, special attention when doing the design of the building. Similarly to point bearings that are applied on discrete foundations, could also support discretely supported ceilings. They could also provide vibration isolation on pile caps, and they could achieve a very low or the lowest natural frequencies possible, i.e. the highest performance. So just to give an overview of where do we fit inside the project, what is our relationship with different stakeholders from a technical perspective. we mainly have to engage with acoustic or dynamic specialists and structural engineers. So usually acoustic and dynamic specialists are responsible for setting the acoustic requirement in a building and mainly the natural frequency of the bearing after they do their own measurements and analysis, vibration prognosis. At the same time, the structural engineer's role is to provide us with the loads that would be acting on the bearings. And by having both input from the acoustic engineer and the structural engineer, we are capable of calculating the optimal material, the optimal elastomeric bearing with the required thickness, with the required stiffnesses, required load capacities to be able to fulfill the acoustic and load requirements. This means that we are fulfilling the comfort criteria and also the safety criteria when we talk about acoustics and also structural input. It is also important to note that all of these bearings must be certified by third parties so that the properties of the products that are being used in the calculations are actually verified in reality. So this way, the safety criteria is also met. I will start with an overview about the case study that we will be presenting today. It is the Opteneo project in Munich, Germany. It is a development with approximately 32,200 square meters of gross floor area above ground, with mainly offices rented out to KPMG and restaurants on the ground floor. There are over 1,100 square meters of roof terraces and loggia. The project developer was Ford and Bauer in Germany. The architect is Nito Sobijano from Madrid and also based in Berlin. The construction period was between 2019 and 2022. The development is actually located in the Munich East train station development, which is used to be an old industrial area, but right now it's becoming the new trendy place in Munich with many mixed-use developments and concert halls. The challenge for developments in that area is that they're very usually close to the railway lines, including the Munich East train station, which is the second largest train station in Munich. This means that the railway lines are at a distance of less than 50 meters from the Opteneo, including a branch line of less than 30 meters. And here we're talking about all kinds of traffic, including freight, passenger, long distance international trains. At the same time, the main source of vibration is the underground Metro Line 5, which is dotted in the orange line you see on the screen. This line is actually 30 meters deep into the ground. And since the Opteneo has around 3 floors underground, this means that the metro tunnel is roughly just 15 meters away from the building. It's also interesting to talk about certain conditions in this project. Here on the screen, you see the footprint of the development in green in the map, close to the railway lines, and also close to the metro line dotted in orange. It actually had a previous building there. There was a previous old building there. And the metro tunnel, which is below that old building, has been there since the 1970s. So it's an old tunnel, and it's no longer the most stable tunnel anymore. This meant that no extra forces on the outer shell of the tunnel were allowed. Therefore, the deconstruction and the construction of this old building had to be carried out gradually in such a way that the loads on top of the tunnel does not change a lot. And this meant to the construction company that they had to, after the deconstruction phase, they had to mobilize the rubble gradually outside of the site so that the loads do not change drastically or quickly on the tunnel during the deconstruction and also the construction phase. A quick overview on the legal situation and the project limits according to the regulations in Germany. I'm not going to go into detail about the acoustic requirements and the acoustic standards. Just briefly, the acoustic consultant in the project, the dynamic specialist, they had to ensure that the vibration levels do not exceed a certain kb value, which is defined and evaluated according to the German standard DIN 4150-2, which relates to the effects of vibrations onto humans. This roughly equates to the limit that was fixed between 0.1 and 0.2, roughly equates to 0.45 millimeter per second in terms of vibration limits. There were also recommendations and guidelines regarding the secondary airborne noise levels, such that the maximum sound level in this project should not exceed 45 dB. Therefore, the dynamic specialist acoustic consultant was brought on board, and the measurements and the prognosis model started in the project. The measurements on site had to be done in 3 stages. The first is on the surface. Right on the surface, there were some vibration measurements that were taken that suggested that the vibration levels are way higher than the limits. Then a second campaign of measurements took place that were done at minus 12 meters, so at the foundation level of the building using drill holes. They also suggested that the vibrations are actually higher than the limits. And then a third campaign of measurements took place after the whole excavation was done, and they actually confirmed the values and the results that were taken in the second campaign of the measurements. In this project, the type of soil is gravel. It's quite stable. At the same time, it transfers vibrations into the building. It was also important to define the frequency spectrum. So the main excitation frequencies are shown on the graph, and it was realized that the main vibrations and the secondary airborne noise were happening at frequencies above than 40 Hertz. In order to reduce the uncertainty in the transmission path, several measurements had to be carried out along the transmission path between the railway and the building. So this is why you see the measurement points MP1 to MP3. And as it can be seen in the graph, the vibration level is actually reduced as the distance from the excitation source, which is the railway, increases up to the building. And this is due to the coupling effect from the soil to the building, which usually leads to further decrease in the vibration velocities. At the same time, due to the coupling effects of the building itself, you can notice an increase in the vibration levels at MP5. And this is because of the coupling effects of the building structure itself, which caused an increase in the vibration levels due to the natural frequencies of the structural slab and the floating screeds. Sorry, no. So it's very important to note something that's super important, that measurements alone are not enough. So the realization of the excitation frequencies and the measurements alone are not enough to define the acoustic requirements and to realize the size of the problem. So after those measurements are taken, these results should always be used as an input in a vibration prognosis, in a model that's made by the dynamic specialist to eventually model the vibration levels and the secondary airborne levels inside the building based on these measurements that were taken on site. And then with this type of model, it is possible to be able to define the expected or the predicted vibration and secondary airborne noise levels in the building, and then define if a solution with an elastic bearing would be required or not, by comparing the results to the actual limits and the actual requirements that are set by the standards. And actually, so this model that is being done by the dynamic specialist in a prognosis depends on the building geometry, the stiffness of the ceilings, the walls, and the building structure, and also the sound insulation measures that are taken into consideration inside the building. So the dynamic specialist in the Optineo project did a prognosis, and here in this table, you're seeing the results without an elastic decoupling. So after they did the measurements in the soil, they modeled the building, they identified the resonance frequencies of the individual elements inside the building, they realized that the maximum sound level at different positions will exceed the required limits of 45 dB in this project. Therefore, the dynamic specialist recommended that at least half of the building is elastically decoupled. And he recommended a solution with a natural frequency of less than or equal to 12.5 hertz. So he did his prognosis, which led to the realization and the definition of the natural frequency requirement of the elastic bearing solution. According to the prognosis results, with the 12.5 hertz elastic decoupling, all the acoustic requirements from vibrations and secondary airborne noise levels will be met inside the building. Now, moving forward to maybe a more to the solution itself, how does it look like on site? What kind of material we're using? Here again, we're showing the building and where the decoupling is happening as a footprint next to the railway line. A quick information about the material that you're gonna see, all the colorful material you're gonna see in the next few slides. This is our brand, Stylodyne, that has been used in this project. It's a polyurethane elastomer. It has pronounced spring characteristics. It's made of closed cellular structure, which means that it could maintain a very high performance even when it's submerged in water. So it doesn't lose its dynamic and static properties even when submerged in water. It's able to maintain its mechanical properties for the lifetime of the structure. And you can see different colors because every color represents a different type of material. Each type of material has a different static load limit. So the materials can withstand up to 24 Newton per millimeter square as load peaks. And they have a very low creep tendency. We also applied our Silomer product line as well. It's very similar to the Stylodyne product line, but with higher damping properties. And it's used mainly in areas where the foundation is for the side mats that are not submerged in water, because it's made of mixed cellular structure instead of closed cellular structure. And it also has different varieties, different colors that represent different types with different static range of uses, up to 1.2 Newton per millimeter square. We also used it in part of the foundation that I will talk about shortly. There are 10 different types of Silomer with also proven long-term behavior and characteristics. So again, we got the requirements from the acoustic consultant, the natural frequency requirements. We got the load input from the structural engineer. So we work closely with both stakeholders to design a material, to eventually create a material proposal that will ensure the comfort, that the comfort levels are met and that safety requirements are also met. Here we're showing a screenshot of the calculations that we have made for the engineer. It's a calculation with full surface bearing. The material selection is made with the loads on the static range of use of the bearing. So there are different types that are installed in different positions depending on the loads that are acting on every position. And in this calculation, the natural frequency of the individual bearing is calculated, and subsequently the average natural frequency in relation to the building, which in this case was calculated to be 11.8 hertz, which means it was less than the required, which was 12.5 hertz by the acoustic engineer. And this means that the product fulfills the requirements. As you notice, silodyne was used because most of the horizontal mats that were applied were submerged in water. The groundwater was around 8 meters below surface level. And silodyne can maintain its performance even when permanently submerged in water. Loss factor is also mentioned in our calculation because it aids in the effectiveness of the isolation because of the difference between the impedance between the soil and the elastic bearing. So I'm going to go through the different levels where the isolation was installed. We're going to start with the, so you can see that the isolation in green, it is covering levels -3 and -2 of the building. Starting with the base level, you could see the different colors of the materials that are applied according to the positions. Each position has different loads, and therefore different materials are applied to be able to withstand this load. Each material, as I said, has a certain color, which refers to a certain type that has a certain static range of use and the static load limit. And we provide this map for ease of installation as well to the site. Here you can see the map with the actual installation on site. The mat is provided in sheets or rolls, and the joints of those sheets are taped with a joint tape so that when concrete is poured, it doesn't pass in between the joints and cause what we call a sound bridge or a vibration bridge. And at this level, the material are installed on a blinding concrete layer. Here you can see another photo where the materials are installed at the base level. A PE foil is installed on top of them, and then a screed layer is installed on top of that. Afterwards, they start with the heavy reinforcement before installing a 3-meter thick slab in that area. Here are additional impressions from the site. The material, as you can see, is very lightweight. Doesn't require skilled labor to install. The materials cover in green, yellow, orange, different geometries, even pits, and it's covering the whole area so that no gaps, no areas remain unisolated. Also in level -3, there were piles because there were piles in some areas because on top of that area there was a 10-story building. So this section of the development had the highest loads. And as we said previously, there's a tunnel beneath this development. So in order not to increase the loads on the tunnel, piles were installed or were constructed in that section in specific to transfer the loads to a lower part of the soil and not in order to avoid activating the outer shell of the tunnel with additional forces. And on top of the piles, so on the pile caps, our stiff bearings were installed that I will show you in the next slide. And the yellow material in between is a soft silomer material in 100 mm thickness that was used mainly to avoid compression force. So this means that the piles were taking the loads alone. The bearing on the pile cap was taking the majority, the main load, and transferring it to the lower parts of the soil to avoid activating the loads on the tunnel, while the infill material in yellow was just used to avoid the compression force. So it wasn't actually taking the loads. And here you can see a better, clearer photo of it from the side. You can see the black dots where the piles are located. And on top of this area is the 10 stories building. In the black dots, we have installed our stiff HRB HS 6000 materials that could withstand 6 Newton per millimeter square in permanent loads. And they're installed as round bearings. And again, as I said, the yellow material is the silomer material used just to avoid the compression forces, to absorb the compression forces. It was compressed by around 25 millimeter. Then on top of that, there's a slab thickness, which is around 3 meters. Here you can see additional photos of the same area. They are, as you can see, materials very easy to handle on site, very lightweight. PE foil being installed, screed being installed on top, and then as you can see at the top of the photo, the reinforcements are also installed on top of the lean concrete. Additional impressions from the site. And here you have clearer pictures of the pile cap and the pile bearing in black, and the yellow infill in Silomer 11 in that area. And this is the section drawing also of that area of the pile cap, showing the pile cap, the HRB bearing on top of the pile cap, the Silomer infill in between the pile caps, and then the PE foil and the lean concrete layer, and then the slab on top. There was also, moving to level -2, there's a very interesting structural aspect of this building, which they called in Germany, the backpack. Because part of the building, there was like a structure that was coming out of the main, let's say, structure, which they hence called it the backpack, as you can see in the photo, because it kind of looks like a backpack. And this was kind of challenging to construct because again the backpack would mean additional loads on the tunnel. So here they had to think of innovative way of building the backpack in a way that the loads are not immediately going to the tunnel. So what's happening here is that the loads are actually being transferred to the piles instead. So instead on being transferred from the backpack directly to the tunnel. And this has been done by first building 4 stories of the building above the surface, so that there's a kind of a balance before introducing the backpack in the other section of the building. And therefore, the loads are now being carried by the slab and the piles instead of being transferred from the backpack to the tunnel and then creating instability in the tunnel. This also, what this meant for us is that the materials that we have to use below the backpack are actually of a softer grade, because we didn't need a material that would need a very high static range of use with very high static load capacities. And with this way of construction, the building will settle just uniformly, because initial studies showed that the piles will settle around 2.5 centimeters, and the backpack will also settle, which wasn't good for the tunnel. So this is why they started building first 4 stories above the ground, and then they built the backpack to avoid the settlement of the backpack and protect the tunnel. Here in this slide, you're seeing the overall isolation. So now we have the full picture complete. We have the isolation of the piles. In level -3, we have the isolation in the base. And we have finally on top, in mostly red color, the isolation of the backpack in level -2. And here we were talking mostly about the horizontal isolation, but it is also important to make sure that the lateral isolation of the sidewalls of the buildings below the ground are also decoupled, because vibrations can transfer also horizontally and then into the building itself. So it was very important to isolate the sidewalls of the building underground. And because of the challenge of the groundwater, it meant that 2 different types of product lines need to be used, because almost half of the sidewalls down to -8 meter were submerged completely in groundwater. So we needed to make sure that the material that's being installed below water could maintain its performance over the long term of the project. And this is why we use silodyne material below ground, and above ground we use the silomer material, which wasn't required to be used below the groundwater level. Finally, we show you the results before and after. So on the right-hand side of the screen, you see the photo of the building after it has been constructed, or almost towards the end, and also the measurements that were taken afterwards prove that the prognosis that was made by the acoustic consultant was actually correct, and the material is performing as per the prognosis. All the vibration and the maximum sound levels are met. And this means that people can work comfortably in the building, that the value of the building is high. You know, the owner of the building, the developer, could rent it out to companies like KPMG without having any complaints, and without KPMG maybe looking for a different office elsewhere because of the continuous, noise problems and vibration problems of the building. So this means that this product, it was an initial investment in the project. At the same time, it increased the value of the building a lot. It allowed the developer to be able to rent out his building and increase the profitability of his asset. And make the best out of it. So thank you for your attention. Yes, so all in all, this is our daily business. So we have been reducing vibrations, solving vibration issues worldwide for the last 55 years in the railway, construction, and industrial sectors. We'd be happy to support you in any way. Thank you so much for your time and your attention. I hope I wasn't too quick. I was just trying to be respectful of the time. If there are any questions, please feel free to ask us. Thank you.
Thank you very much, Omar. Great presentation. Thank you. We're gonna take the questions. Sure. Yeah. You can hear us, right?
They can hear us.
Yeah. So maybe we start with questions from the audience.
So I was discussing that question with Iman. So regarding the body's isolation, normally we have a starter box going up to anchor the reinforcement of the rock foundation. We have seen that circular isolation, the black one. So where the reinforcement one? Or there was no reinforcement?
Okay. Maybe Andreas and Ulrich, maybe you could answer this question.
Can I support?
Yes.
Sorry, can you
Sorry,
hear
guys,
me?
just a second. They cannot hear.
So in pin, they don't provide any reinforcement which is dropping out. Like without.
Can you hear?
It will take only compressive.
Yes, I can hear you, but you can't hear me.
You can hear me, but you cannot hear the colleague.
Yeah, can't hear him.
Okay.
They call pin and
Can you
another
hear
is
me?
fixed.
But
So this they call pin.
can you? Okay.
And also perfect. I saw some drawings, but they are
Sorry, guys, we can't hear you. We're just waiting for the IT to fix the situation. Yeah, maybe.
So I'm not sure if you heard the question here. Maybe I can repeat it. It's about the connection between the piles and the raft. When in the slides, we didn't see any reinforcement passing through, like starter bars, and the pile appears to be no connection. Basically, you've got the elastomeric bearing on top, and then the raft foundation. So the question is, where is the reinforcement? How is this pile working without the starter bars connecting both together?
Can you hear me?
And
Can you
thank
hear
you,
us?
Hammond,
Can
for
you hear us?
attempting to.
No, we can't hear you. Maybe if you could give us 2 minutes.
Okay. Oof. So, sind wir zu zweit.
Hört's aus. Das war jetzt die Frage, warum keine Bewährungsstäbe durchgehen. Ja, ich habe angefangen, das schon ein bisschen im Chat zu beantworten.
Ah, okay, ja.
Hast du den im Blick?
Nee, gar nicht.
Und wir sind nicht zu zweit. Es sind noch ungefähr 20 Teilnehmer online.
Okay, die alle warten. Ja, bin gespannt.
Somebody asks you, we need to share it again. We can.
Can you hear us now?
Yep.
Yes. Yes, we can. Yes, you're right. You're right. Yeah.
Can you hear us?
Yes, we can.
Okay. You say something just so that we test your audio.
Hey,
Hello. Hi.
So we have
Can't
to
hear.
hear.
We can't hear you.
Can you hear
guys.
us? Can you hear us? Hello?
Where you should press the settings here.
Hello?
Actually, the setting. What is speaker this one? No, can you hear us now? Can you try speaking?
Yes, we can hear you. Can you hear us? Hello?
We still can't hear.
We still cannot hear you.
Try speaking.
Can you talk, guys? Can you say something?
yeah,
Yeah,
we
hello.
can.
Okay.
Okay, we can still cannot hear you.
Is mic having issue or any other?
Oh, what a pity.
Both of them will speak like this mic.
Can they hear?
No, this is completely the system. Just one question. If we have your other mic, and if I just remove and keep from my mic, they can hear each other.
Yeah.
I don't just keep it as. Yeah, just like that. It will work, right?
Can you guys talk?
No, I need
Yes.
to change the audio.
Hello?
Next try.
Yeah.
Hello, hello.
Hello?
Okay, wait.
Hello.
They're
Computer
trying
audio.
something else now. Still can't hear you.
Computer audio.
Can you try now, please?
Hello?
Once more.
Can you hear us? Hello?
Without that was
Still cannot
No,
hear you.
it was working. It was actually in the Zoom, right? And that is a microphone audio. Speakers.
Set it here, select it.
Select the speakers. Select that.
Hello? Can you guys talk now?
Hello? Hello?
Once more. Test,
Yep.
test, test.
Hello?
Yes, now it's better.
It's working?
Great.
That's hopefully.
This will work. This will.
So guys, did you hear the question about the piles?
The question is almost imperceptible if it comes from the audience. So if you just repeat the question from the audience, we can hear you loud and clear.
Okay, so the question was that. Sorry? The question about the piles was that there are no rebars passing from the pile cap into the raft. There's only the pile cap and then it stops there. Am I correct? Can you?
Yes, correct. So the question is about, I think it was answered now. It was about
Okay.
the fact that there is no rebar passing between the piles and the raft. There is no starter bars linking the two together. And how is that pile working then without the rebar connecting it? So yeah.
It is absolutely correct. There is no rebar passing from the pile to the foundation slab. But then on the other hand, the pile is designed to take vertical forces only, because all horizontal forces that will occur are transmitted to the soil via the walls of the building. So vertical force transfer is absolutely possible through the elastic bearings. These are designed to take the loads also in an ULS state. So introduction of the loads from the foundation slab to the pile in a vertical direction is still possible, and that's how it works.
And I mean, there are cases where uplifting forces has to be transmitted to the piles. And in this case, so this detail, how it was shown in the project, would not work for uplifting forces. This, so in 99% of the cases, only forces downwards, getting from the raft into the piles. So no reinforcement is needed for that.
Okay, clear. So basically, in the cases where we have that connection that needs rebar, this system cannot be used, and we have to do something else, maybe, right? Because we can't punch
there are different
through
possibilities. You can have rebars with rebar connection for uplifting forces, for example, with elastomeric isolation. But that's more the detail for that is more complicated. It is possible, but not as easy as in this project, of course.
Yeah, sure. All right, thank you.
Thank you.
Another question, yes, please, Declan.
The basement is below the water table. So do you have a waterproofing system in addition to the acoustic system, or was it all in one?
So the question is, I'm not sure if you can hear it. The question is about the basement, which is underwater. Do you have a waterproofing system in addition to the isolation system?
Yes, we do. In certain parts of the building, there has been an additional waterproofing layer. In some parts where the pressure of the water is not as high, it has been made in a way so that the concrete itself can handle the waterproofing. But yes, at level -3, there is an additional waterproofing layer. You cannot use the elastic layer as a waterproofing layer at the same time.
Okay, thank you. Is the waterproofing under the elastomeric bearing to the inside face or the outside face? How do you layer them? Is that the question?
The waterproofing layer is directly connected to the concrete. In fact, there has been used a product that bonds physically to the concrete while the concrete is poured.
Okay.
Waterproofing first, bonding to the wall, and then the elastomeric bearing. Horizontally. So horizontally, is it the same order?
Same layering. So it's concrete, waterproofing, elastic bearing.
Yeah, so first is elastomeric bearing on the base screed, and then waterproofing, and then, yeah, raft foundation. Thank you. Yes, please, a question here.
Can we use this product at source vibration, like when the train is traveling in that time, means fear or something like slightly balance?
Yes, exactly. This is the best way actually to isolate the source. At the same time, you have a lot of existing railway lines that may not be isolated properly. And you may have older railway lines that are existing, and then you have a new development that's being constructed close by to the railway line. This means that the isolation may not exist at the railway line, or maybe it may exist, but it did not consider that there will be such a development coming at a certain distance with a certain sensitivity in the coming years close by it. So, so you have to then isolate the recipient of the vibrations instead of the source in this case.
Yes, please, Mohammed.
Can you integrate this system into seismic design?
Yes, and I would leave the answer to my colleagues. The question is, can we integrate the system with seismic designs?
Shall I answer?
Please do.
The bearings, our materials can transmit seismic forces just as every other structural member of the building. So as long as there are no uplifting forces, just as we had with the rebars in the first question, as long as we don't have uplifting forces, but horizontal forces to the sides of the subsoil, it's no problem to transmit earthquake forces and to fulfill all the requirements for earthquake, to transmit all the earthquake forces. But of course, if we have uplifting forces and we have to pull down the building to the piles, then it's more complicated. But for normal, most situations where you only have horizontal forces to transmit to and vertical forces to be transmitted to the ground, it's not a problem. Yeah, you can do the proofs according to the standards.
Thank you, Ulrich. Another follow-up question.
Yeah, and another one. What are the measurable improvements in the comfort level of those events?
Sorry, what?
Improvements in the comfort level of.
So it depends on the requirements. So we have a wide product portfolio with different performances or different solutions that could be customized based on the building design and based on the requirements that need to be achieved. So based on that, we work closely with the structural engineer and the acoustic engineer to design a bearing that could fulfill any comfort criteria.
And how is it for the company?
It will last the lifetime of the structure. And this is something that we have proven over the last 55 years. So we have a lot of case studies where the material was applied 40 years ago, and it was tested 40 years later, either through vibration measurements or testing its mechanical properties in third-party laboratories. And it shows that the material still fulfills the specs and still maintains its dynamic and mechanical properties over time, because it relies on its cellular structure for its elastic behavior and doesn't rely on artificial softeners or halogens like other type of elastomers.
Yes, please add.
Is this material used already in the United Arab Emirates, and is it obtained the approval of the Dubai municipality?
Yes, it has been used a lot in the United Arab Emirates for many, many years. It's used also to isolate parts of Dubai tram. It's used also in ADNOC projects. It's used in the building sector a lot here. We also have the highest national approval in Germany, the ABZ, which is recognized by the Dubai municipality, and it's approved by the Dubai municipality.
We have used it, if you allow me, we have used it as well in SeaWorld and Dubai. So it's not already for human comfort, it's sometimes for animal comfort.
Yes.
So we were discussing with SeaWorld, and they have said that for some pools, the fish inside the pool, because we have rides there in SeaWorld, we have rides, and those rides, they are fixed on top of the structure. Okay. So they can generate vibrations as well.
Yes.
So those vibrations, when they go through the concrete to the pools, if the animals or the fish can feel a higher level of vibration, they will not swim. They will go to the corner of the pool, and they will stop at the corner of the pool, they will not swim. So they were serious about vibration. SeaWorld, when they are talking to us as a designer, you need to make sure that the vibration which comes from the rides, it will not increase that level, because if it increases, then all the business case of what we are doing for the fish to swim there, it will not work. So it was very, very, very important for us. So we have used a lot of this. I'm not sure if it's the same product or not. That was 5 years ago, 4 years ago, but it's being used. It wasn't used.
Yeah.
If you allow me to take some questions from the Zoom. What's the target frequency for this isolation bearing, especially the surface bearing?
it depends on the criteria we're trying to fulfill, on the type of the building. So if it's a residential building, it's going to be different than a hospital, for example, different than an office building where people are using it only in daytime and not only at night. So there are different acoustic requirements, and based on the acoustic requirements, and based on the measurements and the vibration prognosis to define the natural frequency of the solution, the natural frequency of the product and the system is defined. If my colleagues have a different answer, please feel free to also.
It also depends on the source of vibration, as you said. So different trains, for example, have different or different frequencies that they emit. So this has to be taken into consideration when designing these. But it's also about the soil. So if you have very rigid soil, like a granite slab, for example, it will transmit higher frequencies rather than lower frequencies. On sand, on the opposite, or gravel, you will have lower frequencies also in that spectrum. And well, if you have lower frequencies in the disturbance, you would have to adjust the frequency of the whole system building also to a lower range. So for Germany, for example, it is very common to have frequencies of around 12 Hertz like we had in this year. But if you go to other countries where the soil properties are different, you will have other typical frequencies that are aimed for from a dynamic prognosis for the building.
Thank you, Andreas. Another question from Tariq. 68 decibel is how much acceleration in meter per second square?
I think this cannot be related directly. So since decibel is just a difference between two levels, you cannot really express it as an acceleration. Maybe Ulrich can.
No, it depends on the, yeah, as you said, it's a relative value. So it depends on the every decibel, for every decibel calculation, you have to have a basis value. So for dBV, for velocity decibel, you have the relative value is, I think it's 5 multiplied with 10. Sorry, I can't get this. So with a certain velocity value, it's multiplied, and this basis value is part of the definition of decibel. In every country, that can be different. And for acceleration, I would have to look it up for acceleration, what we use in Europe, but it's different in different countries.
Sure, no problem. Another question from Tariq, it was also one of my questions, Tariq. Are there any products for reducing this vibration in an existing building? Any way we can do with some internal lining maybe of basements or anything that can be done that you have works for existing buildings?
There are a couple of references where existing buildings have been equipped with an elastic layer to the sides of the building below soil level. For the use that we saw here, so if you wanted to equip the foundation layer of the building with some elastic solution, that's practically impossible to do. Depending, of course, on how the source looks like. But for example, if you have a tram line passing close by, then a sidewall insulation may have some benefit. Not necessarily, depends also again on the soil properties, but we have a couple of references where this has yielded quite some beneficial effect for the building.
Actually, we did some test projects on this with only sidewall. So for existing buildings with where we installed sidewall decoupling later on to reduce vibrations. And if you don't go far below the lowest level of the building, only usually it's only possible to go half a meter or a bit more, then the effect is quite limited to 3-4 decibel around this value. And decoupling below the building or in the building, on the walls, on the columns is possible. We have a solution for this, but it's very expensive. So we never It's also patented by Getzner, this solution, but we never did it on an actual building because it's too expensive.
We did it actually.
Really?
There is one single
solution,
reference where a building has been equipped with an elastic layer under the foundation already, but it is a huge effort that has to be taken, and it was really very expensive. But this has been a very prestigious building that has been protected by some arts management program, and so it was worth the effort to do it. Was a big building actually. It has been done, but it's enormous effort.
I'm very sorry, but I have to leave because we have overtime, and I have to get my train, which is the last train I can take. So sorry for that.
Okay, no Thank you very much, Ulrich. Thank you for your contribution.
Thank you. Thanks for having us.
Getting a big clap from the audience. Oh, Andreas is gone also. Andreas is here.
No, I'm not. I'm still here.
Okay.
Okay, so the question from anonymous attendee around the longevity, and I think you've answered that, Omar. It can last as long as the building.
Yes.
Yeah. So
There was a question.
Under tension or shear. So this one was answered as well. Yeah. Can this material is useful for centrifugal and reciprocating forces, reciprocating machines?
Yes. Yes, we actually use it a lot in machine foundation isolation for reciprocating and centrifugal equipment, not only for vibration isolation, but also the material itself, since it acts like a spring. It improves the spring and the dynamic properties of the subgrade. So in many projects like with Aramco and other oil and gas companies in the region and worldwide, we were able to avoid soil replacement under the foundations, while also fulfill the vibration amplitude and the resonance frequency requirements. And I think Hemant knows a lot about this.
Yeah, like Nagaraju is an engineer from Wood. He's working on sale jobs in Iraq. So
very
he
nice.
represents oil and gas.
Sure, it would be very nice to connect with you, Nagaraja, and talk about this maybe in more detail. Because the material can offer a very cost-effective solution and save a lot of time and also construction costs when designing a dynamic machine foundation. There are a lot of case studies on this. For example, Aramco did a cost study, cost analysis, where they realized that by using our material under machine foundations, they could save 60% of the construction schedule to avoid replacing the soil and reduce the cost by 20%, while also maintaining the right dynamic stiffness requirement and resonance and frequency, natural frequency requirement for the foundation without having to do a lot of soil replacement.
Right, thanks.
So Omar, my question is, say in UAE, nowadays we are doing soil improvement using dynamic soil improvement. So if I have a property around and I want to improve that plot, instead of going for a pile foundation, I want to go for like a shallow foundation, and I'm doing ground improvement. Can I use this product to isolate the vibration which is created during construction stage, which may be around 6 months, so I don't disturb the surrounding properties?
Yes, it could be used in a way to decouple the vibrations, as long as you can install it in a manner where you can prevent the vibration transfer through the structure or the ground to the surroundings. So this has to be, discussed in details how it could be done. But theoretically, yes, we can do it using this product because it's an isolator. But it has to be discussed. Not sure if Andreas, you have an idea.
It has been discussed a couple of times. And theory looks nice. Until now, in every single case, practical problems occurred that could not be overcome because construction sites are so extremely dynamic and the landscape changes basically every day, and there is no good spot to install these materials. What you would have to do is to isolate the emission scene, not the emission scene. So not the source. You cannot isolate the source because it's everywhere around the construction site, but you would have to isolate the recipient, and that is also very difficult in construction sites. So yes, it has been discussed. So far, I know of no scenario where it has actually been used to do that.
Thank you. A quick one on you mentioned the linear bearing between floors. You go above the basement. So some of them were seen at column locations. How do you ensure the detailing there where you have rebar going from floor to floor? Is that another special detail here?
Andreas, maybe you could answer that.
You still cannot have any rebar going through. Well, sometimes you can, but in a special way. The main problem that occurs is usually the horizontal forces from wind, for example, that need to be transferred on somehow. You can do that using shear keys. So if you have a profile included in the wall elements that looks like a rectangular shear key, you can use that to transmit the horizontal forces. We had a couple of opportunities where uplifting forces occurred actually between the two stories that needed to be isolated. And it was solved by using steel anchors that had no connection to the structural slab of the top floor, but was rather connected with also an elastic layer underneath the cap of that anchor. So every time the slab was meant to be lifted, it would be limited in its movement by an elastic layer that was able to take all of the lifting forces.
I see. So Andrew, Andreas, in your example that you showed, what was your lateral resisting system? In that case, was it?
Well, we didn't need any lateral resisting system in that case because we had 3 stories of the building underground, which provided enough surface to transfer horizontal forces to the ground.
Mm-hmm.
So the building overground was only 4 stories in the majority of the surface, and 10 stories, which is not a lot really, in one tower above it. So horizontal forces could be completely transferred to the soil via the surface of the 3 underground floors.
Yes, please. Thank you.
Just following up on the same question that you asked. Historically, we provided this continuous joint to allow, for example, the reinforcement to pass through some places, and then most of the place will be isolated. Can we design such way?
Thank you very much for your question. Did you get the question, Andreas, or
no?
Can you hear?
Sorry.
Okay, so the same continuation of the same question. Is it possible to have some of the elements where no rebar are crossing through and decoupling them, whilst others, they are fully monolithic, continuous connection, moment connection? So you have a sort of a hybrid floor.
There were a couple of cases where a part of the building was constructed monolithic and the second part was decoupled. The requirement, if you want to do it that way, is that the monolithic part of the structure needs to be far enough away from the source of vibration, so the levels of vibration are not high enough to be transmitted or high enough to disturb the whole building. Let's put it that way. Of course, this means you need to consider the elasticity of that layer in the structural system for the whole building. So yes, it can be done. Within the part of a building that has to be put on elastic bearings, you should absolutely avoid any kind of noise bridge. There has been some research for this, and it shows that even very little sound bridges, this may be only just a 30mm diameter steel rod going through, already pose an excellent transmission path for vibration. So this is really one of the most important things. If you install this, you need to clearly think about it. Did I catch any bridges that could possibly occur, and to do it very thoroughly, so in order to make it work in the end. So that's really a big issue. Avoid sound bridges of any kind.
Thank you. Any further questions? Last question, please. Yeah.
Existing buildings, nearby methods, how we can solve the problem?
Thank you. I think we touched on this. It's challenging is what I got.
Another question about existing buildings and how do we solve it. So Andreas said it takes enormous effort. There was a project in Germany that took a lot of effort, and it was very expensive. And they only did it because there was protecting some art and some valuable.
The building itself was considered a work of art, and it needed to be conserved. Just to give you a number, it was around about 800 square meters of building footprint, and it took 12 million euros. Not because our materials are that expensive, but because of the structural premonitions that need to be taken. You need to take out all of the soil underneath the building and create a new foundation for the building while supporting it. The goal was the building should not move in the whole process vertically. So movement of the building was limited to 2 millimeters over the whole installation process. So that is really, it's no small feat. It took 2 years of planning and another 2 years of just doing it, because it really, you don't want to do it if it's not absolutely necessary.
Now we understand the reason, Andreas. It may be cheaper to move the train in this case.
Yeah, probably.
All right. Okay.
Last question.
Sorry, we have a hand up, Hamid. I'm sorry.
Just wanted to know if you have come across any application in MMC buildings.
MMC, you mean?
MMC structural.
Modular. Yeah.
You use the project in MMC in any modular concept?
Have you used our solutions in modular construction, Andreas?
Yes, we do all the time. Actually, since modular constructions are often wooden constructions, at least in Europe, that is, but it also works for concrete constructions, the internal sound transmission paths are more prevalent than sound from an external source. So you will have amplification of footfall noise rather than from an external source within modular buildings. And that is something that can be helped if you use the materials in between individual modules. But yes, that's pretty much a standard.
So how do you kind of solve the joint issue between two modules? Because the isolation layer should not break between two modules. How do you solve that joint?
So the question is, how do we solve the joint issue between two modules, because the elastic layer should not break?
It doesn't break. Maybe I misunderstood the question.
I think there are structural joints in MMC when the module is applied into them.
He's saying there are structural joints in the modular construction that maybe create a breakage in the elastic layer.
All right. Yeah, same thing with the elastic bearing of buildings. So there must not be a noise bridge. So any connection that you would normally have in between modules would have to be redesigned to be an elastic connection. There are ways to design these elastic connections, so you can also make it work with pull-off forces, with wind forces or something. A couple of different ones, actually. one I find very elegant to do is to have the modules stacked upon each other with elastic layers in between, and after all have one steel truss going from the bottom to the very top and have it screwed in an elastic way. So they are all bolted together as one unit with only one connecting element, and that is decoupled elastically on the top and on the bottom.
He says thank you, thumbs up. He gives you a thumbs up.
There are a couple of different ways. So if that's some life problem for you, we can discuss this in detail.
Sure, thanks, Andreas.
Okay, Hammond, you had something.
Like I had only a question. Steel, it is strong, but over time it corrodes. Like all material construction, they have some weakness. You are telling it is a perfect, it has no weakness, but like it will be having one weakness that you can say.
They're pushing us to say one weakness.
Well, we have been we try to find one for the past 40 years. Be my guest, join us finding.
This is a challenge for our team here.
He wants us to get fired. Yeah.
Thank you very much for thank you all here, students, committee members, and everyone. Thank you. Please help yourself with the refreshments.
Group photo.
Group photo, of course. Yeah.
Yes, thank you so much for your time.
You're welcome.
Thank
Bye.
you. Have a good evening. Bye.
Thank you, Andreas. Thank you so much.
Thank
Omar.
you.
It's really interesting. You can tell from the question.
Yes.
لا ما بيجي يعني بين هون وهونيك وهيك كثير question.
Thank you. That's great. Great to hear.